So standard 10 current electricity, there is a slight revision of what we have done in standard 9 as well. We'll start with that. So the first thing that we are going to do is for charge. We know that there are two types of basic charges, positive and negative. So the positive one is protons and negative one is electrons. And then when you talk about the magnitude of charge, the smallest possible independent charge is on a proton and an electron, and the magnitude is 1.6 into 10 to the power minus 19 coulomb. So coulomb is the SI unit of charge. SI unit is coulomb. Okay. And uh, a coulomb is a very big unit. As you can see that one electronic charge is 1.6 into 10 to the power minus 19 coulomb. So therefore, one coulomb will be 1 upon 1.6 into 10 to the power minus 19. That is 6.25 into 10 to the power 18 electrons. Okay, it means that if you have so many electrons, okay, how many electrons? 6.25 into 10 to the power 18 electron, then you will have a charge of 1 coulomb. That's a pretty high amount of electrons. And therefore, we use smaller units like 1 nano coulomb will be 10 to the power minus 9 coulomb. Then you have 1 micro coulomb, that is 10 to the power minus 6 coulomb. 1 milli is 10 to the power minus 3. Okay, so these are the smaller units that we use. Okay. Another point that you need to know is the amount of charge is equal to plus minus NE, where N is integer. Okay, so, and this is also called as quantization of charge. It means that charge can only be an integer multiple of charge of an electron. You cannot have 3/4 of electronic charge. You cannot have half of electron charge. You can always have 1 electron charge or 2 electron charge or 3 electron charge and so on. Okay, so that means it is n times 1.6 into 10 to the power minus 19 coulomb. Okay, but because it is very small, we can say that we can have any amount of charge. So current is defined as rate of flow of charge. Okay, so this is defined as rate of flow of charge. Okay, so that means electric current is the amount of charge upon time. So we know that charge is written as Q, time is T, and current is written as I. So that's one formula, that is I equal to Q over T. And if you want to talk in terms of the SI unit, so this is a coulomb. Okay, so COU, coulomb, and this is second. So there is a name for this, and that name is ampere. So that means 1 ampere is 1 coulomb upon 1 second. So this is definition of electric current, rate of flow of charge, and this is definition of an ampere. So that means if you're talking about a charge flowing through a wire, so through a particular cross section, in 1 second, if 1 coulomb of charge is flowing, then we say that the current flowing through a wire is 1 ampere. Okay. So if 1 coulomb of charge flows through 1 second, then the current is said to be 1 ampere. Okay. Again, 1 ampere will have 1 coulomb of charge flowing, and we have just seen that 1 coulomb of charge is a very high amount of charge. So we have smaller unit for ampere as well. So 1 milliamp is 10 to the power minus 3 amperes, and 1 microampere is 10 to the power minus 6 ampere. Okay, so these are smaller units of charge. So again, what you need to remember, this is a formula, and also we have seen that Q is equal to NE. So that can also be one formula. That current is a scalar quantity. So current always flows from positive to negative, while the electrons actually flow from negative to positive. I equal to N1 Q1 plus N2 Q2 upon T. Okay. So what is this note about? Now, when you're talking of an electrolyte, inside an electrolyte, there are two types of charges. One is positive charge and one is negative charge. Okay, so what happens is there are electrodes inside the electrolyte. So the negative charge are flowing in one direction and the positive charge are flowing in the opposite direction. So inside a wire, only electrons are flowing. But inside an electrolyte, there is positive and negative ions, both are flowing. So if we say that one positive ion has a charge Q1 and a negative ion has a charge Q2, and there are N1 number of positive ions and there are N2 number of negative ions, then the total charge, okay, so we can call it as capital Q1, and the total charge over here is capital Q2, will be N1 Q1, and this will be N2 Q2. So this is Q1 plus Q2 upon 2. Again, the same thing. Current is total charge upon time. The electric current is charge upon time. So how do you calculate the total charge? So this is the total positive charge and this is total negative charge. And this is number of positive ions multiplied by charge of one positive ion. This is number of negative ions multiplied by charge on one negative ion. So let us assume that this is a metal sphere and this is an insulator. Okay, this metal sphere has no charge on it. Okay, and let's say this is a positive charge and you're bringing that positive charge and depositing on the sphere. Initially, the work done will be zero because there was no other charge earlier. Now, when you bring another charge and deposit it, work has to be done. And that work done is W1. Then you deposit a third charge, that is W2. Then you deposit another charge. Likewise, you keep depositing charge. That means you're bringing charge from infinity and depositing on this metal sphere. The total work that you do, okay, this total work done to bring a unit charge from infinity to that particular point is stored in the metal sphere in the form of electric potential. Okay, so electric potential is defined as the total work that you do to bring charge. So this is potential is work upon charge. Potential at a point is defined as the amount of work done per unit charge in bringing a positive test charge from infinity to that point. So what does that mean? I'll explain it to you in a different way also. So imagine there is a charge over here, Q. And at a distance R from point Q, there is a point P. And you want to know what is the potential at point P. So from infinity, if you bring a test charge to that particular point, okay, remember, this is a test charge. So the work that you do to bring a test charge from infinity to that point is equal to the potential at that point. Okay, so that is also how you interpret the definition of potential. So potential at a point is the work done to bring a unit charge, a unit test charge from infinity to that particular point. Okay, so we will write potential as work done upon charge. So that will be the definition of potential and the SI unit. So you know that work is measured in joule and charge is measured in coulomb. So potential is measured in volt. Okay, so this will be written as 1 volt is equal to 1 joule upon 1 coulomb. So there you need to know the definition of 1 volt as well. At a distance, there is a point A, and little further away, there is a point B. So at point A, there will be a potential VA, and here there will be a potential VB. So when you're talking about the difference in potential, so when I say potential difference, I mean VA minus VB, potential at A minus potential at B. So say, for example, there is a charge Q over here, and this charge has to be brought from lower potential to higher potential. Work has to be done. Now, this work done, okay, is equal to the potential difference if this charge is 1 unit, okay, or a test charge. So therefore, I'm going to say that VA minus VB is the work done per unit charge. So this is the definition of potential difference. So in potential, we are talking about bringing from infinity, and potential difference, we are talking about bringing it from one point to the other point. The simple fact that you need to remember is whichever of the two ends is more positive is said to be at a higher potential. Okay, and the one which is more negative of the two is of a lower potential.